A couple of things. First up, thanks to the organisers for inviting me. Secondly, I'm going to try and get through about 200 million years of evolution, so it's going to be a fast ride. Hang on to your hats. And thirdly, I'll put in a bit of a spoiler at the start. The whale sharks don't escape GOLT, and that avoids me being put in the naughty chapter of Daniel's next book. So, okay, off we go. What's a whale shark? A very large shark. They've got an enormous body size, and they eat very tiny prey. They eat small tropical krill mostly, and other sorts of small plankton. That means they have to eat an awful lot to support this body size, right? And the problem for them is that they live in oligotrophic oceans. So oligotrophic oceans have warm temperatures and very little food in them. The warm water means that they have high metabolic rates, and that means they're probably going to have some very strong selection for cost-efficient foraging. How do they forage? Well, you can see here the water comes in the mouth, and basically there are these plates here. You can see a close-up of them that lie over the gill, and they filter out effectively the food that's coming in through the mouth. So we put some accelerometer tags on whale sharks, and we looked at their foraging, and this is what we found. Basically, they do an awful lot of gliding, particularly on descents. They essentially glide down as they descend, getting free filter feeding on the way, and when they come up, they have a very short and steep return to the surface, so these very asymmetric dives. The other thing they do is they swim incredibly slowly for such a large animal. And together, these tactics increase the foraging efficiency for the animal by about 22 to 32%, we calculate, compared to if they simply swam along on the surface with their mouths open. Okay, what's life like in the open ocean for a whale shark? So here's a tag we've got returned from a whale shark. We've recovered it, and it's got a detailed pattern of its dive record. So I've just these hatched areas are night, the clear areas are day, and we're just looking at what the whale shark's doing in a day versus what it's doing at night. So if we just expand that out and we look a little bit more closely, we can see that during the day, the whale shark's spending a long time on the surface and then descending right down to here, about 400, somewhere between 300 to 500 meters or so, and then coming back up and spending a long time on the surface. At night, they're hanging around the thermocline. So they're doing something different between day and night. What are they likely to be doing? Well, out in the open ocean, of course, there's a diel vertical migration of planktonic food, and down at that 200 to 500 meter mark, there's a deep scattering layer. And our satellite tagging is clearly showing that the whale sharks are following this migration. Now, the problem for whale sharks, of course, is that once they get down there, they're in deep cold water, and that water could be anything up to 20 degrees cooler than the surface, the water they're experiencing at the surface. What does that mean for the sharks? Well, they're foraging with a gill, and so the gill will cook, because they're using that water influx across the gill to forage. It means it's likely to cool the blood pretty quickly. So this data here shows that the mean minimum dive temperature is correlated, quite well correlated, with the amount of times they spend on the surface after a bout of diving. So effectively, what they're doing is they're going down to deep water, they're having to then spend a period of time on the surface, basking to warm back up again. All right, so how do whale sharks actually deal with this? Well, they have a specialised body plan as well. Here's a whale shark on a dock in China, and it's being cut in half with a giant saw here. And what we can see is that it has an enormously thick skin. In fact, whale sharks have a skin that's one of the thickest in the animal kingdom, about 20 centimetres, about a hand span at its thickest points. But under that, we have a layer of red muscle, and this is the red muscle that's used for routine movement, right? So it's very thin, and it's lying right at the surface of the body. Below that, we have these massive blocks of very poorly vascularized white muscle. So it's like a giant chicken, if you like. And below that, we have the oil-rich liver, which of course is the buoyancy support for the animal. And that liver is probably insulating the rest of the body and the central nervous system there from the cold water and the cold food that it's ingesting into its body. Okay, so we've got two selective forces then counteracting each other in whale sharks. We've got the need for cost-effective foraging, and moving so slowly, it means they can't generate internal heat like a tuna. They've got and their option, what they do instead, is they store that environmental heat they're gathering at the surface using a body plan adapted for thermal inertia. And the active muscle is kept away from the body core on the surface of close to the surface of the body. And thermal inertia really explains the large size of these things, and they do get very big. The largest ones ever reliably measured were 43 metric tons and over 18 metres long. So these animals can get really, really big. So effectively what they're doing is a life history strategy of gigantothermy, and it's one that reptiles have used for a very long time, including the sauropod dinosaurs, some of the largest terrestrial vertebrates ever to exist, and used today by leatherback turtles as well. Okay. So that body plan then is just a little contrast here, contrasting it to tunas and to laminid sharks. Here's our whale shark. Here in the whale shark, all the active tissue, all the active muscles on the outside. Here in the tunas and the sharks, it's all kept close to the body core, and of course they've got a ret system for exchanging heat with the blood. Okay, so we've got whale sharks up to 18 metres long. The next question is, well, could they actually get any bigger? And are whale sharks nailed there by GOLT and a bunch of other potential limitations to their size? Well, why don't we take a look back in the fossil record and see what that can tell us about size in filter-feeding fishes in the past. Now, there's lots of ideas about published in literature about limits to size for fishes. A paper by Freeman and Noakes in 2002 sort of listed many of these. There's lack of support from an ossified skeleton. Fish get so big they simply can't support themselves in the water. Growth rates are simply too slow. If you start from a very small size, a tiny larvae, it's very difficult to get to a very big size. And in fact, of course, that you're spawned from eggs, so you have very tiny eggs to start with. And of course, there's Dan's hypothesis with GOLT, that you're limited in size by effectively the oxygen that can be supplied by the gill. So what happens if we look back in time? Well, if we go right back to, in fact, to the Cretaceous in the Mesozoic, the oceans were dominated for over 100 million years by these things, pachycormid fishes. They were a giant filter-feeding fish that evolved in the mid-Jurassic and was present right through to the KT boundary. These things were amazing. They grew at incredible rates, and you can age them using, actually from the fossils, looking at the spines, the fin ray spines, quite incredibly. They grew up to 16 metres long as a reasonable estimate for their size. Today, what have we got in comparably? Well, the largest filter-feeding teleost we've got out there is this thing. It's a paddlefish, and this is one of the record, it exists in relic habitats and lakes and rivers, and this is one of the largest ones ever caught, 45 kilos. Clearly not a patch on a pachycormid, right? So pachycormids then, they grew to 1.6 metres in their first year of existence. That's a faster growth rate than a tuna. Their bones were poorly ossified. They spawned eggs, and at larger sizes, they had a growth rate roughly equivalent to whale sharks and basking sharks today. They grew to very large sizes, and they lived in warm, highly productive oceans. Okay, there were also planktivorous sharks around at the same time. In fact, mostly, of course, what preserves when it comes to shark is their teeth. And so there's these, what we call sand tigers sharks. If you were in the States, grey nurse sharks if you're in Australia, and they appear through the fossil record in dibs and dabs. But really, there's been findings of some incredible elasmobranchs, filter-feeding elasmobranchs just recently, like this enormous shark that actually was an equivalent of a manta ray, effectively. So there were plenty of sharks doing filter feeding around at the same time that the pachycormids were in the oceans. Of course, everything was going swimmingly, as it was, as you could say, but then, of course, this happened at the KT boundary. What happened then? Well, the pachycormids are extinct, but what we saw then was the rise of elasmobranch filter feeders. We have the manta rays, the whale sharks, basking sharks, and the megamouth shark. In fact, though, as it turns out, the megamouth shark also appears in the fossil record down here. So maybe one of the few filter feeder elasmobranchs that actually made it across that boundary. Whale sharks getting around 18 metres, basking sharks around 12, megamouth about 5. And they all arose in the early Paleocene, late Paleocene, early Eocene, when the seas were extremely warm. Today, of course, we've got lots of these filter feeders, big ones in the oceans. What happened, though, to the teleost filter feeders? Where did they go? Why didn't they make it across? Why don't we have some giant teleost filter feeders today? The teleost filter feeders certainly made it across the boundary. There are lots of filter feeding teleosts today, but they're generally small sizes. Think of an anchovy, right? Okay. And then, of course, later on, around the same time, we have the rise of the mammals as filter feeders in the world's oceans. From these toothed relatives into baleen whales, again in the Eocene. And what some people don't know about the evolution of whales is pretty interesting. There were a lot more genera in the past. And yet around sort of 12 million years ago, when the continents separated and we set up the westerly wind circulation around Antarctica and the ice caps formed, the oceans cooled down remarkably. And that precipitated the loss of many of these genera of whales. At the same time, around 3 to 5 million years ago, whales massively increased in size. And that coincided with the land bridge across the Panama to South America, the disruption of circulation around the world, circulation of warm tropical waters, and a rapid cooling of the world's oceans. They became very stratified by temperature, and that happened extremely rapidly. It also set up highly productive upwelling systems off the west coasts of continents. So what do we look at then today? Well, we've got humpback whales, for example, a baleen whale, and pachycormorants here, a whale shark, basking shark, manta ray, and a megamouth shark. Interestingly, all of these things, irrespective of how they're breathing, whether it's a lung or a gill, whether they're a teleost or whether they're an elasmobranch, reached around the same size. What's the deduction from that? Well, what that implies is that it's not intrinsic traits and phylogeny that are setting the limits to the size of whale sharks, but rather that it's the mechanics of filter feeding and ocean productivity that actually set those size limits. But of course, whale sharks and humpback whales aren't the biggest filter feeders out there. These things, blue whales, are. And this is a bowhead whale. It's roughly the same size as a whale shark, but it's actually 3 times the mass. And it lives in cool water, highly productive, cool temperate oceans, polar oceans as well. So how do blue whales get away with being a filter feeder? Well, they've developed a specialised morphology for gathering enormous amounts of prey in a single gulp. This lunge filter feeding. And Jeremy Goldbogen's done an awful lot of work with this. Basically, he suggests that blue whales have now reached their maximum size that they can reach, essentially because of the energetic cost of engulfing and filtering these enormous amounts of water that it does. Okay, so I don't know where I am on the timing. Oh, pretty good. Okay, all right. So will whale sharks keep growing in size? Well, not unless there's a marked change in productivity in marine systems that they can take some advantage of, or there's some form of morphological innovation. What whale sharks do is they don't really escape the GOLT. They actually use it. They use those poorly vascularized blocks of muscle inside their bodies to effectively warm themselves up and use thermal inertia to cope with how they have to survive out in an open ocean. So warming oceans, you've just heard this before, warming oceans may be a real threat if filter feeders are actually existing at metabolic limits. Some say they're existing on a knife edge, an energetic knife edge. We have a lot of interesting questions about what happened to the teleost filter feeders. But we used to think that there were no filter feeding reptiles back in the Mesozoic. Turns out there were lots. There were actually lots of ichthyosaurs that were enormous filter feeders. And a recent fossil from China, a recently published paper, You'll never guess what size it got to. It got to 20 metres and fits exactly into the scheme here of around 18 to 20 metres. So I should have put the ichthyosaur up there, but anyway, that's kind of where we're at. I'll call it quits there. Thanks.